I know. We want to analyze it right now. Come to 0 period. Come after school. We'll have a powwow with someone this weekend. But here we go. We are in section 3.3. We are talking about increasing. Wait. The functions just increase with a straight line? Or in a straight line? No, they can increase concave up, or they can increase concave down. So why am I showing increase with a straight line? Anybody know?
It's simple. It's the slope.
It's simpler, and we're talking about the slopes. We know a function is increasing, is rising, if the slopes of the function, aka, slopes of the function, what are those called? Derivatives. If the derivatives are positive. If the derivatives are positive, the slope is pushing up, the function is increasing. So how do I know if a function is decreasing?
It's negative.
Don't put it though. What's negative? Derivative. AP graders, one of the things they hate the most is the word it, because it can refer to all sorts of things. So you have to be precise. So when the derivative is positive, the function is increasing. When the derivative is negative, a function is decreasing. Okay, so how do we take a function, no graph? Ooh, can you guys read it? X over x minus 1. How do we take a function, no graph? And we're not allowed to use our graphing calculator, and we can't necessarily get the graph precisely on our own just by looking at it. How do we figure out where it's increasing and where it's decreasing? These steps. Because, as I showed you yesterday, if we can consider the domain, number one, check for discontinuities, check the domain. If we can consider the domain, if we can find the critical numbers, then we can make a sign chart, which is what I refer to down here. We can make a sign chart where we put in whatever those domain or those discontinuities are, whatever those critical numbers are. Maybe there's 3, maybe there's 1, maybe there's 2. And then we can go ahead and test the sign of f prime to tell us about the behavior of f. And at the end of the day, we'll be able to say, hey, on this interval, from negative infinity to him, or from him to him, or from him to him, or from him to positive infinity, we can say what's going on as far as where the function is increasing or decreasing. So let's go ahead and start back at the beginning. We need to, first of all, before we do anything else, talk about the domain. Kiddos, what is the domain of this function? Good, denominator. Cannot be 0. So x cannot equal 1. Are we okay? Denominator can't equal 0, x cannot equal 1. Critical numbers, I cannot find them until I derive. Right? So where is most of the work-intensive part going to come? Taking derivatives. And that's how section 3.3 and 3.4 both are, because 3.3 means the first derivative. 3.4 needs a second derivative. But to get to a second, you have to take the first. Okay, so are we hearing this out?
Yes.
All right, so we're going to practice our derivative skills at the same time. So f prime of x equals bottom minus
top bottom. All over bottom square.
Perfect. The name of the game is not just taking the derivative, but also simplifying, which is sometimes even harder than taking.
Okay.
X minus x, I get negative 1. Okay. Has anybody double checked me? Negative 1 over x minus 1 squared.
That's good.
Perfect. What am I going to do with this derivative?
Set it equal to 0.
Set 0. Set equal to 0, both the top and the bottom. But wait, can the top equal 0?
No.
Negative 1 can't equal 0. I can't even find an x. This is impossible. So forget him. There are no zeros of this derivative. No horizontal tangents. Set the bottom equal to 0. Okay, there's one. But pause. What do we already know about the domain?
It can't equal 1.
So I'm going to put this in parentheses. Yes, we're going to include it, but there is no derivative here either. I mean, the derivative does not exist. It's a DNE. It's a denominator. But the reason it does not exist, yes, because of the derivative, but also the function isn't even there. And if we want to be super snazzy back in pre-cal, we wouldn't just say x cannot equal 1. We would say there's a vertical asymptote at x equals 1. Do you guys remember why? It's in the bottom, and what can't you do? You can't remove. If it was removable, it'd be a whole. Anyway. We have a vertical asymptote of x equals 1, so of course there can't be a derivative there. Okay, so our critical numbers, we can put x equals 1, but we'll actually just put none because we already have the domain, so we're not going to add in anything else. So when we make our sign chart, we're using negative infinity to positive infinity. This number line is symbolizing x values. Remember, increasing, decreasing, how left to how right? We're using x intervals to describe. Okay, this is showing our x intervals or our x values. How a sign chart works is we're trying to figure out, yeah, the only value we're going to put on is, all right, people in the back. Behavior, sorry, that came out wrong. The only value we're going to put on is 1. It's the only number that I got from my critical numbers in my domain. Technically, if you want to be super snazzy, eventually I'm going to have you put a little like, that way you remember it's not existing at 1.
Wait, so
Okay.
even though it can't equal 1, you have to put 1?
Well, we're still going to put 1 because think of it this way. Whatever's going on the left of 1 could be doing one thing, and on the right of 1 could be doing something else. The 1 splits the graph somehow. Now, here's the deal. Remember Strictly Monotonic, the boring teacher in a movie? Okay, only doing one thing. As soon as you mark up or you split up your number line with domain and critical numbers, the entire region on one side or the other of each of the separations will be strictly monotonic, which is awesome, because that means I don't have to test all the different places. I just have to pick 1. What's some number to the left of 1?
0.
Perfect. Let's plug it in. But wait, what do we need to know the sign of before we can figure out the behavior of? Sign of. So I'm going to go ahead and plug in what is f prime of 0. Taking f prime, plugging in 0, it's going to be negative 1 over 0 minus 1, negative 1 squared.
1.
What's the sign? Negative. This entire interval, the derivative will always be negative, which means the function will always be decreasing. Now, I'm not making that a curved up or a curved down decrease. You can decrease either in a concave up way or in a concave down way. But we haven't learned about concavity. That's section 3.4. That needs a second derivative. So all we're saying now is, I don't know, the tangent lines are going down. Function's decreasing. Okay, so what do you guys think I'm going to do over here? Yeah, and what's something you can plug in? 10, sure. 2 works too. 3.71829, I'm making up numbers, works also. Pick something easy. 2? All right, 2. Although 10 wouldn't be totally bad. Plugging into the first derivative, negative 1 over 2 minus 1, oh, that's positive squared, right? So a negative over a positive is a... Is this function increasing anywhere? And the answer is no. So when we go to say where is it increasing and where is it decreasing, or what are the intervals for which?
It's decreasing in both.
Yeah, it's decreasing in both. So we're going to say there are no intervals. None.
Do you have to split up the
Yes.
decreasing?
Because if you don't split up,
that means you're saying that 1 exists.
and 1 does not exist. So we have to split up at 1. So this is where we go back to the domain x can't be 1. There's a vertical asymptote at 1. When I put my decreasing, how far left on the number line? Negative infinity. How far right? 1.
Oh.
Not including 1. There's a vertical asymptote there.
So then would it be 1 and
Exactly. How far left? 1. How far right?
negative?
Oop.
Or just positive?
Good, good, good.
Okay.
Dun, 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 dun.
Do you have to do the little U thing?
You can put a comma, you can put the word and. Technically or is a little bit better, but yeah, I just do the little u because it's fast. It's a little u and simple. You guys get the idea then?
Yes, we do.
So, yeah, definitely. Check the domain. Find the critical numbers. Oh, you can't do that until you find the derivative. Find the zeros and the DMEs of the derivative. Put them all, collect them. There was only one. Collect them, put them all on the number line.
Yes.
It separates the number line into intervals. All we have to do is test 1 point in the derivative in every interval, because that whole interval will be doing the same thing. And then you have your final answer. Answering how far left and how far right. So, how about the polynomial?
Oh.
Do you guys need to see the steps, or can I zoom in on the example?
You can zoom in.
Okay. Polynomial, as you write it down. Same thing. Where is it increasing? Where is it decreasing? x to the fourth minus 10x squared plus 9. X to the fourth minus 10x squared plus 9.
It exists everywhere. So,
What's Sean doing when he says it exists everywhere? He's checking the domain. Good.
Critical numbers.
We could say negative infinity to infinity, meaning no discontinuities. My critical numbers, my crit numbers, you guys will make fun of, that's okay. I can't do it until I,
divide.
okay, cool. Who's already found me a derivative?
4x squared minus 20x.
Good, 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 good. DMEs, there aren't any, there's no denominator. So all I have to do is just set equal to, does that make sense? No DMEs, set equal to 0.
Square root of 5.
Should we go adding that 20x?
No,
Good.
pull out a
Factor.
4x.
Oh.
Factor. Factor, factor, factor. What do we have left? I think it's an x squared minus 5. Do you guys agree?
Yes.
Okay.
So 0, so we have to set both.
Because what you're doing is, for those that don't see it, when you factor, you gotta set all the factors equal to 0. So set this one equal to 0, and set this one equal to 0, yeah? Okay, what do you get coming out of that?
X equals 0, X
Plus or minus square root of 5.
0 plus or minus the square root of 5.
Okay, is everybody caught up? First one, 4x equals 0, solve x equals 0. X squared minus 5 equals 0.
Plus or minus 5.
Plus or minus square root, good. Second? Okay, what do we do with all these? Make a number. Now, eventually you guys might just put f prime on top, and you might put f on the bottom. But for right now, I want you to write sign of and behavior of. The sign of the derivative indicates how f is moving and changing, increasing and decreasing. But I cannot use the positive negative of f prime. I cannot use those words to say positive negative of
Bless
f.
you.
Just be careful. I'm putting in my, bless you, 0, negative root 5, positive root 5. Now pause, I just heard, no one answer. I just heard, what is root 5? Now, pause, we don't really need to know.
It's like
Pause, don't tell me! We don't need to really know what root 5 is, we just need to know around what root 5 is. Someone tell me the lowest or the nearest perfect root that's below root 5.
4.
Root 4. And who's that?
2.
2.
2.2.
Tell me the next root that you know.
9.
And what's root 9?
3.
So what is root 5? I don't know, but it's something in between. If you want to guess, don't do 2.9. Because it's closer to 4. I'd do like maybe 2.12. Test. I don't know, just guess. It's 2 point something. So question, with 2 point something, can you pick a number in between?
1.
Yeah. Let's figure out what is f prime of negative 1. F prime of positive 1. What's something bigger than 2 point something? 3, 4, 10,
3.
20, 100? 3. We did not need to know. Now, in homework, could there be a nasty root that you kind of need to look at because you're not quite sure and you find a decimal? Okay. But as best you can, think mental math. And just approximate. All we need to do is figure out something in between.
So do we plug this in?
So we're plugging in for all of this?
Because we'll know what the original function is doing, increasing or decreasing, if we can find the sign of the derivative. So it's all about positive or negative when you plug in here. Okay, Sean, do you already have one for me?
No, I was just wondering, do we
Pause, who wants to plug in negative 3? Nathan, you have negative 3, negative 1.
I got it.
David, negative 1, you're plugging in. You're plugging in positive 1. Austin, you're plugging in 3. Get me a sign. Go ahead, question, Sean.
No, that answers my question. I was just wondering if we could just plug in signs of the numbers, but I guess not.
Depending on the value, especially with the polynomial. But in this one, we could almost just plug in, because a negative squared, well, we have to know whether that's negative or positive.
It's quite positive for mine.
Positive, and you were positive 1, right?
Yeah. No, it's negative 1.
Oh, negative.
Negative.
Oh. And then on yours was
Negative.
negative. Austin's is positive.
And I was, wait, shoot. -3 is -27 times 4 is -2.
Negative, that's the
So
point.
it's po-
You don't need to know the number,
Wait,
remember?
Wait, but that's not done,
Oh, that's
the
okay.
-60, it's positive. Yeah, no.
They plug in the
Yes,
derivative?
Yes, it's positive.
They plug in the derivative?
Yes.
Pause. Hey kiddos, is it easier to plug into this with a cubed and a 20,
Oh, oops.
or to plug into this?
Oh, that would've been easier.
No, it's okay, we learn from our mistakes. They're not mistakes, it wasn't a mistake. Shortcut. If I plug into here, can't I say a negative times is always a negative, or a positive times is always a positive? And then think about this multiplication, or this factor. So for instance, -3 squared is positive 9, right? 9 minus 5 is 4. Whatever, a positive times a negative is a, that's how I knew. If I plug in -1, negative times, but -1, that's 1 minus 5 is negative. A negative times a negative is a positive. I'm not saying it's always that easy, but you don't have to go back to this form. You can plug in the factors to make it easy. Long story short, question.
Up, down, down.
Exactly.
Or down, up, down, up.
Careful. Decreasing, increasing, decreasing,
So how would
increasing.
you write that down?
Ah.
You never put the square brackets, right? But, well, I mean, you might, but like, you don't here, right? Because
When you are solving, let's get down to intervals first, Tyler, and then I'm going to answer that. Don't let me forget. Increasing, decreasing. So who can tell me a decreasing interval? Good. How far left? Negative infinity all the way up to?
-5.
Good. And let's keep going. Let's get the other one. Where's the other decrease?
Negative infinity to,
Oh, careful, careful.
positive infinity to 0.
Oh, but not for decreasing, no. Sorry. Decreasing. 0. How far left? √5. How far right? So find the decreasing part, and then say how far left? 0, before it goes to increasing. How far right? √5. It's bound between those two markers.
Okay.
What would the increasing be? What's the first increasing interval? Negative √5
To 0.
to 0. Right? And then √5
Positive
to...
infinity.
Good.
it's actually really cool.
Alright, that's not that bad.
Like, are there any functions?
If you guys know polynomials, maybe you can guess it's going to be one of those W-ish types.
Oh,
Looks like
the only time that it would
Now, Tyler is asking a very particular question, and it's good. He's saying, will we ever close the intervals?
Oh, bracket.
Not at critical numbers, because we can only close it if we're saying it's decreasing or increasing there. But the whole point of a critical number, isn't it an in-between point?
Mhm.
It's a 0 or a DNE, it's not positive or negative. So it's a neither, remember? So if it's a critical number, we have to leave it open. If it's a domain problem like the vertical asymptote, we have to leave it open. It's not even existing there. So the only time we would ever close this is if they gave us some sort of funky graph where an endpoint was a place where the derivative was negative, or the endpoint was a place where the derivative was positive. Then I'd have to close it and say, well, the derivative is negative there, or the derivative is positive there. But when I'm doing it, I'm using critical numbers and domain to split up, and they need to stay open. Does that make sense, Heidi? Whew. Oh, hey, look, it's a W. But we're not getting the entire graph. This is section 3.5. But how would we get the whole graph? Well, for critical numbers, negative √5 and positive √5, which is 1, 2-ish, and 1, 2-ish, we would have to find the y values. So at negative √5, positive √5, we'd find the y values. At 0, we'd find the y value. We'd say, oh, sweet, decrease, increase, decrease, increase. Dun, 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 dun. What else could we do? We could find the x-intercepts. We could find the y-intercepts. We could even figure out the concavity, concave up, then down, then up. But that's not until section 3.5. Okay. The second part of our section. The second part of our section. There was, remember the long title for section 3.3? The increasing and decreasing test and the first derivative test for relative extrema. Whew. Here's part 2. The first derivative test for relative extrema. How to find relative extrema with the first derivative. And the reason why we have to have that whole title is there is a way to find relative extrema with the second derivative also. But that's section 3.4.
Why is everything in chapter 3?
Huh?
Why is everything through graphs in chapter 3?
Because it's applications of derivatives, and so they spend 5 sections saying, all right, let's talk about everything with graphing and derivatives. And guys, I am going to get the box in just a second, but first of all, I need you guys to highlight. Let x equals c be a critical number of f. I need you to highlight. Let x equals c be a critical number of f. I haven't totally figured out what homework's going to look like over Thanksgiving. It's not going to be a lot, but I can't just have you forgetting all your forever cards. Over Christmas break, over spring break, there is something called a forever card quoting assignment. Some people last year chose to write it, 1 time fully written equaled 2 times quoting. Some people it's easier to say things over and over again, or easier, it's better for their memory, we should say. It's not about easiness. Some people, it's better for their memory to actually write it out on my paper. I'm probably going to do something similar to that over Thanksgiving break. And so in my head right now, I'm debating, do I make you have all these forever cards memorized by the test? Or do we have a forever quiz when we come back after the test? After the break, sorry. After the break. I'm still debating. I want to do what's most useful for you. But make sure you get these forever cards written in, because if I choose to let Thanksgiving break be a forever, make sure we have it solid time with a forever quiz right after the break, maybe you can use your forevers on the test.
Or what?
Maybe. But I have to think of what I think is best for you. But get those forever cards updated. Remember we're trying to cram in by Thanksgiving? Maybe we don't really have time for a forever quiz before that. And maybe it's not so much by the test whether you know exactly what the forevers are, but you do need to know how to use them. So keep them close. Get them written down. The first derivative test for relative extrema says, first of all, let x equals c be a critical number. Huh?
This doesn't seem so hard.
It'll make sense, like especially with that W graph on the one before.
That one was nice.
Yeah. The decreasing to increasing where it changed was a relative min, and the increasing to decreasing where it changed was a relative max. And the decreasing to increasing was another relative min. That's basically the idea of this test right here.
Oh, do you include like domain restrictions in your sign chart?
In your sign chart, yes, but you have to keep in mind they are domain restrictions, which means they cannot be relative extrema. And hence where it starts to get tricky. If f prime changes from negative to positive, then f has a relative min. If f changes from positive to negative, then f has a relative max.
Oh, that's why you put the little
But
dot in.
only at critical numbers. I'm not saying domain restrictions, I'm saying only at critical numbers. If f prime does not change sign at c, then there is neither a relative min nor a relative max at that point. Yeah, this should be 24.
Wait, so which was 23?
23 was the increasing decreasing test. 22 was, I think, mean value theorem. 21 was rolls. Absolute extrema was 20.
And then
If it helps, you can also put in f changes from increasing to decreasing. My visual people, if f prime changes, oh, I put it wrong. Cosiento, negative to positive. Hold on, if f prime is negative, what's f doing?
It's going down. It's going down.
Negative, it's going down. Does it make sense there would be a relative min? And either it'd be at a sharp point, that's a relative min, a DNE, part of a critical number, or smooth turn, that's a relative min. But it only happens at critical numbers. It won't happen on a vertical asymptote, or on a hole. It's It's only gonna happen at critical numbers. So how could I change this one? F prime changes from positive to negative. What's another way of saying that?
Let's change from decreasing
Good,
to decreasing.
good. So my visual people, that should help you think about, like this is when hand motions in calc will be nice. They're like, oh, positive derivative, F is increasing, negative derivative, oh yeah, there's a max, I see it, right there. Maybe it's sharp, if it's a DNE, maybe it's smooth if it's not. But right down here at the bottom says, be careful. F has to exist at that point. To be a critical number, this cannot be a domain restriction. No discontinuities. I'm going to underline it. I'm not going to make you write it in your forever card, but I'm going to tell you right now that
Just cross it out.
about 1/3 of you is going to get confused and tricked because you do.
I don't think you're moving that.
I know. I'm trying to get back to where it needs to be. Because you will forget that a discontinuity is what it is.
I try and say.
But F does not have to be differentiable. It could be a sharp point. But we know that. Critical numbers, whatever, they can be DNE or zero. Zeros of the derivative. Okay, so with the first derivative test for relative extrema, let's see how a question like this could look. If you guys want to write down the steps, I suppose you can. I'm going to probably rearrange this slide in just a second. Basically, check out what it says. Do a sign chart. So do all the steps we just wrote, and then analyze it. Oh, look at it? Yeah. Look where for relative extrema? Only at the critical numbers. Only at the crits, right? Look only at the crits. Look only at the critical numbers, not the discontinuities. Okay.
You're a terrible person.
If you guys want to sketch this, I suppose you can again. But check it on a sign chart. Check it on a sign chart. This would be my critical number, right? That's my C. The derivative's going to be a negative to a positive. What's going to exist there? A relative min. Does that make sense? Okay, this one, sign chart. Here's my C. My derivative's going to be a positive then a negative. What's going to exist there? A relative max. But what if I have a sign chart? And it goes, the derivative goes positive to positive. Do I have anything? No. No relative min or max. And it's a point of inflection, maybe. But no relative min, no relative max. And then what if I have a sign chart? Negative, negative. Do I have anything? No. So, there must be a sign change in the derivative at a critical point to have a relative extrema. We could almost take that whole first derivative test for relative extrema and replace it with that one statement. We could almost have it. There must be a sign change. So let's go ahead and do some practice. The goal, find relative extrema. To do it, find or make a sign chart.
Removable.
No, there's nothing removable.
For the first derivative test, that's not really like, it's just like a rule, but it's not a test, right? Because wouldn't you just be doing the same thing you did in the last one?
Well, increasing, decreasing test, remember, just tells us how to know where a function is increasing, decreasing. That's it. The first derivative test says take all that. And now let's look at it, analyze it, and see from the sign chart, hey, cool, where are my mins and maxes?
Okay.
Does that make sense?
Yeah. We still only do the critical number
No, we still have to make a increasing, decreasing, but remember, relative mins and maxes cannot occur at domain restrictions. Why is Charlotte asking that? It's a great question. What's the domain of this guy? X cannot equal. So I'm going to put plus or minus 3 in my sign chart. I have to for the increasing, decreasing.
And then also 0, right?
But I just have to remember, plus or minus 3 cannot be a min or max. It's a domain restriction.
Yeah, what are the other ones?
Yeah, that's 0.
Well, hold on. Have we found the derivative yet?
No.
Okay. Kiddos, in your homework, let me give you something real quick for those of you that haven't started. When you get to any of these problems where they give you a function, you have to find a derivative. If you want, in your homework, you can have on one part of your spiral. You can have where you're doing like the problems, showing the sign chart, all the work. But if you want, on a separate paper or even like a separate page of your spiral, you can say, this is my derivative workspace. And couldn't you say, hey, number 1, here's the derivative, number 4, here's the derivative, number 9, here's the derivative. You could go through and find all the derivatives. And then you can say, all right, whew, all that's done. Let's go use them all. Now, not every homework question means for you to do the entire sign chart. But anyone that asks you to find increasing or decreasing intervals or relative extrema from functions, they're expecting you to take a derivative. If you want, you can separate that from your problem and say, okay, I'm going to do all my derivatives over here. That's good for 3.3 and 3.4. And then you can go ahead and just take the nice pretty version. For instance, if you were to do this one, the derivative, I'm not teaching you the quotient rule. What if I just gave it to you?
Squared on the top, right?
You have
Should cancel
bottom d
out.
top, should be 2x cubed minus top d bottom. The 2x cubed cancels. And then you have negative 9x squared.
Over, you know,
Over
back
x
of
squared
that
minus
out,
x
you wanna
squared.
simplify it more.
Yeah, here's have negative 18x.
Plus 81.
Now careful. What if your homework, you have all these magical little derivatives that showed up and there's no work anywhere, no workspace to your homework? Either you cheated and went to Wolfram Alpha and typed it in, or you cheated from CalcChat, or you did amazing mental math, and that's not always possible, so
It is, it's always possible.
just letting you know.
Keep trying.
What are the critical numbers, cool kids?
No more.
Good. We have at x equals 0 from this guy. And then we set the bottom equal to 0. Oh, wait a minute, but that's at x equals plus or minus 3. Don't we already have those? Okay, x can't equal that. So remember, we already have plus or minus 3. So the only new one we're going to add in is x equals 0. We're going to make our sign chart.
Oh, so you can't put in the difference.
Exactly. We are going to put in our negative 3. We're going to put in our positive 3. But are you guys okay if I put little parentheses symbolizing, those are discontinuities? Is that okay?
Sure. Let's do like the dotted.
You can do the dotted lines too. They are technically vertical asymptotes. So either way, whether you do the parentheses or the dotted lines, you don't technically need to do both. But I need the sign of f prime on top. I need the behavior of f on bottom. Has anybody plugged in negative 4 yet?
So positive.
Yes, it's going to be positive. Why? How did I do that so fast?
This is the negative.
Negative times a negative is a positive. Anything squared is a positive. I don't need to know the number, just the sign. What if I plug in negative 1? Negative times a negative is a, positive over positive. Or if I plug in positive 1? A negative over. No, if I plug in 4? A negative over a positive.
Got it.
So I have increasing, increasing, decreasing, decreasing. Now,
Are they usually points of inflection if they're like that, or
usually.
Okay.
Usually. Tyler's talking about the negative 3, positive 3. Remember, they weren't allowed to be relative extrema anyway. But in this one, would we have even said they were? No, there was no change. So we were safe, but in other problems, there might be a change at a discontinuity, and you're like, yeah, it's a relative. No, it's not. It's a discontinuity. The question, what's going on at x equals 0? Follow it. Follow the flow.
It's maximum.
And we already know that it's a 0, so not only do we know it's a relative max, we know it's a smooth turn relative max. Dun to dun dun.
Well, you don't have to put any like increasing or decreasing.
No. Because they just said in the problem, just identify the relative extrema. So from the sign chart, we can say, booyah, dun 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 dun.
So I know if it's a point, if it's an absolute value, right?
Say it one more time.
Or like a sharp point?
Oh, if it comes out of the DNEs. Oh, remember? If it comes out of the DNE. If it's a 0, we know it's going to be a nice, smooth, horizontal tangent. Okay, because I don't mind us stopping right there. But can we recap what we did today?
Yes.
We were able to take a function, no graph, and by checking the domain, taking the derivative and finding the critical numbers, we were able to make a sign chart where we could analyze with those discontinuities and with those critical numbers the intervals where the function is going up and going down. increasing and decreasing, without meeting the graph at all. Then we said, cool, if we have that information, we can go ahead and look at that sign chart. Find relative mins and maxes, as long as we remember they can never occur at discontinuities. They can only occur at the break. Bye, cool kids. See you later. Happy birthday, Sarah. You guys were all here. You're 17 today?
Can I come in just for a test question? Can I come in just to get one-on-one test questions?
That works. I should have the copies by then, hopefully.
Alright, awesome.
Alright, Dirk, you ready for that business class?
Bible, dude.
Yes.